All right, anyway, we were talking about NFAs. Let's talk some more. NFAs. This is non-deterministic finite automata. They are like DFAs, only the main difference is they can have several outgoing arrows for each state. So like for example, here is a NFA. NFAs also can have what we call epsilon transitions or spontaneous transitions, if you want to be fancy about it. How about that? This is an example of an NFA. And you will notice that from each state, there may be several outgoing arrows with the same label. Like for instance, from this state in the middle, there are 2 outgoing A arrows. From this state over here, there are no outgoing arrows at all. That is allowed. And over here, there's no outgoing B. There's also this epsilon arrow from the first state, which means from the first state, you can just go over here without using up any letter when you're reading a string. And what does it mean for a string to be accepted? So any individual string could actually end up in several different places depending on how you decide to read the letters, because you have several choices for which arrows to follow. And so what makes a string accepted? A string is accepted when any of its final states is accepting. I mean, when you read through a string, there are several different ways you could do it. If any of those ways is an accepting state, then that string counts as accepted. And if none of its strings are accepting, then it is rejected. All right? So for example, in that NFA right now, so this one here, this accepts. Can someone shout it out? Give me an example of a string which is accepted here. Nobody wants to shout. A, yeah, great. If you start here, A is accepted, right? Or something like AA, you could go A and then another A. Or you could do epsilon and then AA, right? Those are 2 ways of reading A. Or you could go A and then A. So anyway, what's accepted? A, AA is accepted. Is the empty string accepted? I think it is, because you could start here and then do epsilon and end up here without having read anything. So the empty string is accepted. Also something like A, B is accepted, because you can go A and then B and end up back here, all right? Can anyone say what's rejected here? Is anything rejected? The only rejecting state is there, but I already said the empty string is accepted because you can go across here. Actually, there are some strings that are rejected here. Any thoughts? Yeah? Something like BB, yeah. In fact, any string that begins with B, well, actually, that's not quite true. You can go epsilon and then B, but you can't do another B, right? This NFA can only accept, as far as strings with B's in them, it can only have a B if it's the last letter, I think, just by looking at this. You can't ever do a B and then followed by something else. So this rejects BB. Yeah, what I just said is not quite true. I said it only accepts if the B is the last letter. But even so, some of those are still not accepted here. All right. This rejects BB. I think the language overall accepted by this is something like A to the N B. I think that is the language. A to the N B, or maybe just A to the N. Yeah, it's a little complicated because A to the N is accepted because you could just stop over here, or you could do one B at the end, and that would be accepted also. But anyway, I'm not trying to get into all that. I'm just giving some examples of what it accepts and what it rejects. All right. Great. I would like to talk for today, and we're only going to talk about this for today and then move on to some other things. Let's talk about the formal description of an NFA. And it is very similar to a DFA. It's just like there are a few details that are a little bit different. So the formal description, and then we're going to try to write some proofs by induction just in a couple of examples. Formal description of NFA, all right? I'm going to say it's basically the same as a DFA, so it has the same 5 ingredients: the states, the alphabet, the transitions, the starting state, and the accepting states. The only difference is the details about like exactly how the transitions work. That's the main difference. So I'm just as a preliminary, this is really the same as DFA, except the 2 main differences are, first of all, in an NFA, you can do these epsilon transitions. So the first thing is we allow epsilon transitions. That means that the arrows, they can be labeled with A's and B's, whatever letters, but they can also be labeled by epsilon. So that's one extra thing. And then also the business about several outgoing arrows. So the other rule is for each state S, let's say, if I do something like delta of S comma A, what that means, of course, is if I start in state S and I read the letter A, what state do I go to? But the thing is, in an NFA, it could be more than one state that you go to, or it could be no states that you go to. So the answer here, this is a set of states, not a single state. That's because there may be several outgoing arrows with the same letter. So when I ask you, like, if you start in state S and you look at it and you read an A, where does it go to? The answer could be it goes to like this one and also this one. Or maybe it could be it goes nowhere. That would be the empty set, right? So anyway, this transition here, the answer that you get out of this is not a state, but it's a set of states. That's really the major difference between DFA and NFA. All right, so let's try and write down. I'm going to write down, this is the formal definition of an NFA. It is this kind of 5-tuple, just like a DFA is. And I will use the same notation. So Q, sigma, delta, Q naught, and F, where Q is a finite set of states. Of course, it must be finite. That's important. That's what the F stands for in NFA. Q is a finite set of states. Sigma is the alphabet. Delta is the transition function. And I will write, as usual, the domain and codomain of delta. And this actually is where the NFA definition looks quite a bit more complicated. But maybe I'll refresh our memory. For DFAs, this said delta, you don't have to write this part, but just so that we remember. Delta goes from Q cross sigma to Q. Remember, what that means is what you plug in as the inputs to delta are a pair, state, comma, letter. That's why it looks like that, right? And in a DFA, this says the answer is just a single state. And this is what needs to be changed for NFAs. So there are actually 2 changes that we need to make. First of all, instead of letters here, in the second part of the pair when you plug in, you can plug in a letter, but you're also allowed to plug in epsilon, right? Because there are these epsilon arrows. So the first modification is I'm going to say instead of Q cross sigma, it's this. And this looks crazy, but this is how it has to be. Q cross sigma union epsilon. So that means instead of just the letters, which would be sigma, it's the letters or maybe epsilon. And this is, in terms of set theory, this is how you have to write that. Sigma union the set of epsilon. So this means when you plug in pairs, the first thing in the pair is a state. The second thing is either a letter or it's epsilon. All right? And then the answer, and this is the other part of, this is the other detail. So maybe I'll just try and do a little commentary here. Here it is letter or epsilon, right? That's what that weird little union is doing. And then the answer, instead of Here, I said the answer goes Q. The codomain of this function is Q. That means the answer that you get out is a state. But this time, I need it so that the answer I get out is a set of states. In other words, a subset of Q. And the way to write that is like this. That is a fancy P. This is called the power set of Q. This is something I hope you remember from your discrete math class. That says the power set. The power set. That is the set of all subsets of Q. So what this means is what you plug in is this pair, and what you get as an answer is a subset of Q. And that's what we want, a set of states. So the power set of Q, this is the set of all subsets of Q. Sometimes that's written as 2 to the power Q. I prefer this fancy looking P there, power set of Q. All right? So this is complicated looking, although we don't really have to think in these terms very often, but this is really the difference between DFA and NFA. It's the structure of this transition function. The things you plug in are pairs where the second thing could be a letter or epsilon, and the answers you get are sets of states, not individual states. That's the difference. And these sets, of course, they could be the empty set sometimes, and we'll see. They will be. All right, can we finish the description here? I got through Q, sigma, delta. Q naught and F are what you think they are. So Q naught is an element of Q, and it is the starting state. And F is a subset of Q, and it is the set of accepting states. All right, and here ends the formal description of what an NFA is. Totally the same as DFA, except for the structure of the transition function is more complicated looking. All right. I thought maybe we could write down. So this is just like for DFAs. It's always going to be very easy, but you'll see a homework problem or so about like, here's an NFA. Can you write the formal description of this NFA? There may be a quiz question to this effect. Be sure you remember what I'm talking about. It's not hard at all, provided that you remember what I'm talking about when I say the formal description. So here is an NFA. Let's write the formal description of this NFA. All right. So in order to do this, we need names for the states because I need to refer to them when I write all the details out. So let's call these STU, stew. All right. And so my machine is M equals. First thing is the set of states. STU is the set of states. Next is the alphabet. That's just A's and B's. Here's a little technicality. You should not write epsilon as part of the alphabet. Remember, epsilon means the empty string. It's not a letter of the alphabet. Epsilon is just a notation which represents the empty string. Even though you see an epsilon as one of the labels here, that doesn't mean epsilon is one of the letters in the alphabet. Epsilon just is a special notation for the empty string. Okay, then delta, which I will describe below. Then T, what's next? The starting state, that is S. And the set of accepting states is T and U as a set. Like that. All right, and now I'm going to say where, and then give all the values of delta. Now, it's a little important. So when I was grading the quizzes, there was a question like this on the quiz about DFAs. I didn't take off points for this, but you should be, if you want to be correct, these guys out here should be ordinary, like curvy parentheses, not the set things, because this is an ordered 5-tuple. The ordering matters, of course. Those are the states, and that's the alphabet. If you wrote them the other way around, it would mean A, B are the names of the states, and STU is the alphabet. Yeah.
Is it acceptable to, instead of having the curly brackets in there, you just like do Q sigma, and then you say where Q equals.
Yeah, sure. Yeah, some people wrote, and this is totally fine, you could just write Q sigma delta whatever, and then down here say where Q equals whatever. That's totally fine if you want to do it that way. Yeah. But anyway, these should be the curvy parentheses, and then these things should, the first thing, the second thing, and the last thing should be sets. This should be just a single element that is a single state S. So don't put the set of S here. That's technically not right. It's just S. But this is the set of T and U. Okay, anyway, where? I got to say all the values of delta. So I'm going to say delta of S and A is, what do you say? From S, where does the A arrow go? And the answer is T. But because of the technicalities of the function delta, it should be written as the set containing T, because in an NFA, the answer of the transition function is always a set, not a single state. Now, sometimes it is just going to be a single state, but it still needs to be inside of a set. All right, delta of S and B. That means if I start in S, where does the B arrow go? And the answer is there ain't no B arrow, so it does not go to any states, which means I put the empty set here. All right. The empty set, you could also write this as that, a set with nothing in it, right? Those are the same. Don't write this. That's different. That's the set containing the empty set, which is not what you mean. You mean the empty set, so don't write that. I'm going to scribble it out again. It looks like a double negative if I say not and then I X it out. So I scribbled it out again. That's three total negatives, just to make it sure. So yeah, put the empty set like this, not the set of the empty set. And finally, I have to do a delta of S and epsilon. Where's the epsilon arrow from S? And the answer is it goes to T. It should be the set of T. Because it could be that there's more than one epsilon arrow, and in that case, you'd have to put them all in a set. All right? And then, and so on. Maybe I'll try and put them over here just so I don't have to scroll. I also get delta of T and A. What do you think for delta of T and A? Yeah? U? Maybe I should scroll a little.
Oh.
Does that change your mind?
Yeah.
It should be T and U.
Yeah.
T has two outgoing A arrows, so it is the set T and U, right? Delta of T and B, there's only one B arrow and it goes to U, so this is the set of U. And delta of T and epsilon, there are no epsilon arrows, so this is the empty set. And then finally, the U arrows. And actually, there are no arrows at all outgoing from U. And so those are all going to be empty sets. So delta of UA is the empty set. Delta of UB is the empty set. Delta of U and epsilon is the empty set. There you go. All right. That's because there are no arrows outgoing from A, from U. So I got to put empty sets everywhere. All right, any questions about that? There's no surprises, I don't think. Just you got to sort of get the details right. But it's not hard. All right. What about, so, eventually I want to talk about what is actually the formal definition of the language that is accepted by the machine. In order to talk about that, we should discuss, we also have delta star, right? Remember in a DFA, delta star is the one where you read through a whole string and see where that ends up, all right? And we had that, delta star is what you really need to use when you're trying to prove that a DFA accepts certain types of strings. And it's the same for the NFA. So the delta star is really super important. And the meaning of this, so for a string X, delta star of S and X in an NFA. Now in a DFA, I would just say this is whatever the state is that you end up when you read X. But in an NFA, of course, there are many different arrows you could follow to read any given string. And this delta star of SX is defined to be the set of all the states that are reachable by reading X. So this delta star of SX is the set of all states reachable from S when we read X. All right. Because there's multiple arrows, there are several different places you could end up, and this delta star is sort of the union of all of those different places. It's the set of all of those different ones together. All right. So, for example, could we just say, for example, with this same one again? I'm going to just say some particular values of this delta star thing. So here, delta star of S and AAB. That means if you start in state S and you read AAB, where can you end up? And I would say, well, what do you think? Yeah. U. Yeah, I agree. U. I think when she said U, I could hear it in the tone of her voice. What she means is the set containing U, right? It should be a set. Now, in this case, it happens that, U is the only place you could end up. But technically speaking, this ought to be written as the set containing U. Yeah, how about delta star of S and AA? What do you think of that? Somebody else, tell me. Maybe someone I haven't heard from. I think you just don't want to say it. You want to say it? The set of T and U. Excellent. He even said the S word. Set. That's the S word I'm referring to. The set of T and U. Yeah, great. If you read AA, you could either end up in T or U. Or how about delta star of S and epsilon? This one is a little weird, maybe. If you start in state S and you read the empty string, that is, you don't read any letters, where could you end up? Any thoughts? I think this is I would say S and T. That's what I'm going to say. So T, because you could start here and do the epsilon arrow and end up in T, certainly. But you could also start here and do nothing. That's what the empty string means. So reading the empty string from here means do nothing. Now this epsilon arrow is kind of optional. If you want to, you can go across here without reading anything. But you don't have to, so you could just stay here. So anyway, that's why you get S and T as the two states you could reach using the empty string. All right. This is actually different from in a DFA, if you recall, delta star of S with the empty string is always equal to S automatically, but that's not necessarily true in an NFA because of these epsilon arrows. All right, etc. I hope everybody is hip with the delta star. All right, it's the set of all states that you can get to. Okay, so then we can say what is the definition of the language accepted by the DFA, the NFA, is, all right, something like that. The language of M, if M is the name of the DFA. It should be all the strings which are accepted by the NFA. So I want to say something like all strings X in sigma star, such that X is accepted. That means when you read X from the starting string, one of those things that it can end up is an accepting state. So I'm going to say this kind of in words a little bit. Delta star of Q0, remember that's the name of the starting state, and X, I will say it this way, contains some state in F. Remember, F is the set of all accepting states. So you have to write this out. You know, in a DFA, you just say this equals F, or is an element of F, but that's not appropriate anymore because this thing here is a set of states, and what determines if X is accepted or not is if this set of states contains one of the accepting states. And so you have to write it like that. All right, this is a little bit cumbersome to work with, this definition, but you can actually write this if you want to look fancy. If this was sort of a Hollywood production, I would always write in the fanciest possible way. This is the same way to say the same thing. Contains some state from F. Another way of saying that is that one element of F is also in this set. Another way of saying that is that the intersection with F is not the empty set. So this is maximally awesome looking if you think that kind of thing is awesome looking. This is the definition with no words. Nobody likes words, right? Not in Hollywood productions. This is the definition of the language accepted by the NFA. This, in ordinary words, means if I start in the starting state and I read X, then that set and the accepting states, they have some common element, which is to say this contains one of the accepting states. All right. Excellent. What I want to do today is just a couple of examples of an NFA, and then you prove by induction that this or that string is accepted on the NFA. Unfortunately, for that, we need our, sorry, I just got rid of it. There we go. What about, this is sort of the last ingredient. What about what I'll refer to as delta star of S and XY property? This, remember, was the basic step that you use in those proofs by induction. It is a weird step. I'll write it for the DFAs, and this will require some modification because of the details of how the deltas work. But I hope everybody remembers. For the DFAs, it looks like this. Delta star of delta star Sx, comma, y, right? That's and this looks crazy, but it's actually very much the key step in all of those proofs. Everybody knows this by now, since we've done a bunch of those. That's what it looks like for a DFA. Unfortunately, you cannot write that same thing for an NFA, and the problem is right here. In an NFA, that is a set, right? Delta star of something something is a set of states, which means this is no longer appropriate to plug in as the first coordinate of another delta star, all right? Because the thing that you plug into another delta star would be just a state, not a set of states. So in an NFA, this is a set, so we can't plug it directly into another delta star. That means for an NFA, we're going to have to rephrase this rule. So there is a similar rule. It's the same idea, only unfortunately it has to look quite a bit more complicated. And I'm going to write down what the version, sort of the NFA version of that property is, and then I'll see if we can explain it. The NFA version is like this. I will say if T is an element of delta star S and X, then delta star of T and Y is a subset of delta star S, X, Y. This is the rule. Unfortunately, is a bit more cumbersome than the other one. The other one was a fairly weird equation, but at least it had an equal sign, and you could just sort of substitute stuff, right? This one, in my opinion, is more of a pain to work with. But can we unpack sort of what all of this says? It says, so this is about if I start in S and I do X followed by Y. And what this says is, okay, if I start in S and do X first, and I can end up at T there, then all the states continuing from T when I do Y, those are part of the states where if you started X, you did X, Y. All right. It is really the same idea as that rule from the DFAs. It's just because these things are sets rather than individual states, it has to look more complicated like this. And you will see there's a more convenient form to write this in. So in our proofs, it's actually easier. You have no reason to believe me when I say this, but it's actually easier to write them sort of backwards. So usually the way that we use this is going to be more like if delta star of Sx contains t as an element. I'm going to write it that way with a sort of backwards element sign. So this just means t is an element of that delta star, only I'm writing it the other way around. It's because, and then, well, I'll just finish writing. Then I'm going to write the other one the other way also. Delta star S comma xy contains as a set delta star of t and y. All right. It turns out this, you'll see when we write these proofs, it's easier to write the proofs down if you write them in that way. If you write it this way, you can more or less copy our sort of structure for the DFA proofs using these element signs and subsets rather than equal signs. All right, let's try one. I don't know if we have enough time, but I got certainly enough time for one. I have one for you all to try. Maybe we'll have to start off next time with one for you all to try. All right, so let's try. I have a new example here. How about this? This is a NFA. Tried to make it all nice. I noticed that some of you on your homeworks or whatever, you make sure on your iPad to draw perfect circles every time. I appreciate that. I hope you don't think less of me that I don't do that. It just takes too long. But I just spent like 30 seconds telling you a stupid story about how you all make perfect circles. I could have been doing that, but I didn't. Okay, this is my NFA. Your job, as usual in these problems, is first of all, tell me what is the language that's accepted, and then prove that those strings really are accepted on this NFA. This is the NFA. So this accepts. Can anyone tell me like a formula? You know, A to the N, B to the N, something like that? It's not A to the N, B to the N, but. Yeah? B to the N, A, B, he said. I like that. B to the N, A, B, right? You start over here, of course. You can do a bunch of B's if you want, but if you want to get to the accepted state, you have to do whatever, all those B's, and then A and B, and that's it. All right? Excellent. So this is what I want to prove, so I'm going to prove it. Formally speaking, what I am saying is B to the N, A, B is accepted. What I mean by that is delta star of S, B to the N, A, B. And here's where you will see. I'm not using an equal sign here. It contains U as an element. U is an accepting state. You should not say equals U because that thing cannot equal U. That thing equals a set of states. What I care about is that that set of states contains U as an element, because U is the accepting state. All right? We're going to prove this by induction. It goes similar to our other proofs by induction, only basically we're never going to use equal signs. You always have to use these element signs or the set, subset signs. And it works out nicely if you write them kind of backwards in this way. Anyway, let's try it. So I'm going to, as usual, proof by induction by N, by induction on N. So I'm going to do the base case, which is N equals 0. This always goes fairly easily. I want to show delta star S, B to the 0, A, B contains U. All right, and what does that mean? Delta star of S, B to the 0, A, B, of course, is equal to delta star of S and A, B. And what is delta star of S and A, B? Well, you look at the diagram. Starting in state S, if you do A followed by B, it is U. Now, technically, this equals the set U. but the set U does indeed contain U as an element, all right? And that's what I wanted to show. So this is sort of just a weird little technicality here. This delta star, its answer must be a set. In this case, it is the set containing only U. And that set containing U, of course, one of its elements is U. So that's what that means. And this is what we wanted to show. So I'll put a little check there. All right? And the induction step. We assume, this is our induction hypothesis, delta star of S b to the k a b contains U as an element. And then I want to show that same thing but with a k plus 1. Delta star of S b to the k plus 1 a b contains U as an element. All right. And here is where we get a little tricky. So we're going to have to use this. I mean, it's the same idea as the other proof, but unfortunately, because of the way the delta star rule works, you have to write this in a somewhat weird order. Maybe I will, hopefully you can see this nicely in your notes. This is the property that we're going to use of this delta function. Maybe I'll just bring it down here. All right, this is my little, I'll put that over there as a sidebar. That's what we're going to use to make this proof work. Now you have to decide for yourself what is going to play the role of x and y, right? And the x and the y are always sort of how we break the string up. We usually consider this thing here, and you sort of break up one part of it into the x part and the other part of it into the y part. And because I know how these things typically go, and you all know this too, I'm going to break off one b from the front. That's because I like, it says b to the k plus 1 ab. I like to see b to the k ab, right? So this part right here, I'm going to write as b followed by b to the k ab. And this is going to be my x and y, right? That's going to be my x and y. Now, I intend to use the stuff in the box there, all right? The box is a little if-then. It says if delta star of s and x contains t, then this business contains this business, all right? So first of all, we should figure out what is delta star of s and x. So here, my delta star of s, now I'm not going to write x, I'm going to write b, right? Because b is playing the role of x in this proof. What is that? Well, we can look on the picture. That is just when I start in state S, it's S again, right? Now, technically, it is the set containing S. So this has as its element S, right? And so now I'm going to use the stuff in the box. So by the box, I'm using the stuff in the box where x is little b, y is b to the k a b, s is s, and apparently t is also s, right? I hope this isn't too confusing. I'm using the box here where I begin with delta star of sx contains t as an element. Here I have delta star of sb contains s. So I'm plugging in everything in the box where x is b, y is b to the k a b, and s and the big S and the big T are both big S. So by the box, it will say now, then delta star S, okay, xy is b to the k a b, contains delta star of t, but t is s, and y is b to the k a b. All right. In my opinion, using that thing in the box is much harder than it was for a DFA. It's the same idea, but it's just because of the way the sets work, it's a lot more complicated. All right. Anyway, can we continue from there? I have this is now contains this. Does anyone see what we can do with that? This is actually something that we know something about from earlier in the proof. Yeah? Yeah, right. This thing from here contains U. So I can say this contains U. And that step right there was the induction hypothesis. All right? And what do you get if you read this all the way across? So from the left, so this means delta star S. Now instead of B to the K, AB, I'll write it as B to the K plus 1, AB. All the way across contains U. And this is what we had to show, right? That's what it says at the very top, was what we wanted to show.